Okay, good afternoon everyone. So let's start. We'll still give the other display some time to warm up, but in the meantime, one announcement is online question set 3 is ready and it has been released just shortly, I think. Yeah. So yeah, you should be able to all see it and working on it. Okay, hopefully it will come on. All right, so let's continue our discussion of regression. Last time we talked about linear regression, and we briefly discussed some extensions, which we'll talk about in more detail to linear regression, right? So in linear regression, we specifically had talked about the least squares estimator, and then we talked about how you can think of the least squares estimator. First, how you can solve it. One is by simply using the normal equations and inverting our matrix. Then we also talked about when that matrix is invertible or not, and what you might do if it's not invertible. Even if it's invertible, it might be very large to invert, so you could resort to techniques like gradient descent, right? And if it's not invertible, or even otherwise, you can resort to regularization, right? Where you matrix that you are inverting and add in a little bit of some diagonal elements, right? So we added in lambda times I, if you remember, and that helped us do the inversion because it boosted our eigenvalues and made them non-zero, right? So that's just a recap of what we talked about last time. And we saw that you can think of the regularization as actually a map estimate under a Gaussian model, whereas the simple least squares estimator was MLE estimate under the Gaussian model. Okay, so that was all last time. And then briefly we had talked about what you can do beyond linear regression, where we talked about polynomial regression that we'll go over again. And we'll talk about regression with general nonlinear features. And then get to some questions like, so we'll talk about more nonlinear techniques like kernelized regression and Gaussian process regression today in class. But in between, we'll stop and sort of ponder over this issue of Biasvariance trade-off, which is related to model selection. How do you choose the right order of the polynomial, right? That's just one issue that comes up in regression, but you have seen model selection issues come up earlier, right? About wherever you have to choose a parameter. How do you tune lambda? How do you pick the C parameter in SVMs, right? So there are lots of places you had to make choices of what parameters should go into your algorithm. And model selection is essentially about picking those parameters correctly. And some insight into what the parameter value should be is given by a Biasvariance kind of decomposition. So we'll look at that in the context of regression today, okay? And then we'll go back to some more nonlinear techniques. And I also wanted to mention, this is something we won't cover right now, but we'll talk about it again when we go to non-parametric methods, which is also another thing called kernel regression. And that's going to be different than the kernelized regression that we'll talk about today, but we'll get to it later on. And that's about doing local regression. But this won't come until later when we talk about more non-parametric methods. Okay, so that's stuff for later. Just give me a second to bring the screen down. Okay. All right. So let's start talking about, here's a recap of polynomial regression. So last time we had talked about that in linear regression, you just assume your prediction f of x, right, for the label for x is just beta naught plus beta 1x, single feature. Right? And if you have a single feature, but you want to now fit a polynomial to your data, not just a line, then you throw in x terms like x squared and so on up to x to the m, where m is the degree of the polynomial you want to fit. And we can still write this as x times beta the same way as we did for linear regression, now just thinking that now your feature set has expanded, and instead of having only one feature, you have one x squared up to x to the m as different features that you are using in your linear regression. So you can still call it linear because you can sort of write it as x times beta, just a linear combination of your features, but your feature set has not expanded to include these nonlinear terms. Okay? And beta 1 to beta m is now the set of your coefficients. And now you can resort to, because we can write it down in the same formulation as for linear regression, you can resort to the same kind of techniques we used earlier, which is if your matrix is invertible, you can just get your regression coefficients by a closed form expression given by this, right? And if it's not invertible, you can throw in some regularization by a diagonal term, right? So this is some lambda, adding lambdas to the diagonals of this matrix and now inverting that. and you can get back your regression coefficients, which in this case would be the MLE estimate, and in this case would be the map estimate, right, under a particular model that we discussed last time. And your prediction is just going to be now x times beta hat, where beta hat is either one of these, whichever one you choose to be, and x is the set of features for your test point. So your test point is simply little x or unbolded x, right? But when you are trying to do the prediction, you are going to write it again as 1x squared x to the m, all the expanded set of features, right? And then multiply it with your regression coefficients to do the prediction. And yeah, again here, A is similarly the set of the expanded feature set for all your training data point, the first data point up to the nth data point, right? So this is just revising what we did last time. Everybody okay with this? Any questions on this part? No? And this was all, remember, this is still only for a single feature. So you can still do polynomial regression with multiple features, except now your feature set kind of goes on expanding. Now you have one linear term for every feature, each of the p features. But if you're trying to do, say, quadratic approximation, then you also have these quadratic terms corresponding to products of the different terms, right? So you have xi's and xj's, all possible one of these. If you're doing third order, you include the and so on up to degree n, right? And again, you can form a giant A matrix. And similarly, for the test point, you can form a long vector x, which will now include all the features and their, right? And you can still employ the whole, all this machinery we learned for linear regression. Of course, as you have more and more features, you will not be able to use this solution as much, because this is only valid when n is to discuss. The number of training points is larger than the number of features. And if you're going to these higher and higher order polynomials, then you will have a very large set. You may not have enough data points. So you will have to resort to regularization, which is the second solution we talked about. Okay. And I think I showed you this last time, but here's the blue is the underlying function from which some data is generated by just taking some random draws from it and adding Gaussian noise. So you can see it better if you print out these slides, but these are the training points here, some little circles you can see. And this is just trying to fit different order polynomials to them. So this is fitting a 1 order or degree polynomial, which is, I guess, order. Yeah, so k corresponds to order. 1 order means 0 degree, which is just a constant. So fitting a constant, fitting a line, fitting a quadratic, right, 7th order polynomial. And you can see that the fit kind of seems to get better and then worse, right? Going from the constant to a line to this, maybe the fit is actually getting better and better. But as you go over here, you see that you tend to get very large sort of deviations, and that's maybe not, again, going back to a bad fit, right? So there's a sweet spot in the middle where you have a very good complexity of your approximating function. And the question is, how do we sort of get to that, right? So that's we don't, in some sense, want to overfit by increasing the order of our polynomial too much. Yes?
Positive and negative infinities as the limit says. So if you have a flat function like that blue line, how are you ever going to
It's actually, so here it's actually not a flat function, it's still this function.
Okay.
Right? So if you look at the scale, that has changed quite a lot. So here it was 0 to 1.5, right? So your blue function lies in that. And this is not a constant function. This is just the same function squished down. Or another way to think of it is, if I zoomed in to still have the same axes, the pink function would overshoot. And as you said, it will go to...
What happens outside the frame of this?
It can overshoot at the sides. It can also sort of be overfitting in the middle, where it kind of wiggles around a lot to fit those data points well. Okay. Right? Yeah. So actually, I have a code for this. I can maybe put it online if you want to just play with it and zoom in on different parts and see what the function look like. Yeah, maybe I'll do that. I'll put the code and then you can play with it. It's simple routine in MATLAB. Any other questions? Okay, so let's look at this issue of the bias variance. This model selection, as I said, there's like a sweet spot where your model has the right complexity and then it gets worse before and after it. And one way to look at it is what's going on is, let's compare two fits. So let's compare this, say, the constant fit versus this very high large degree polynomial fit to still our underlying function. The ground truth here is the blue line. Okay? And we'll see that what happens, clearly we have a very good fit to our data points here. So in some sense, we are doing better in terms of approximation. but we'll see that our fit is going to be very unstable, which means if instead of these particular samples, I take another sample, the same function, so the same function but new draws from Gaussian noise added to it, or sampled at a new set of values, then you will see that for the low degree polynomial, in this case just a constant, the fit is quite stable, right? So even if these points have actually changed from one figure to the next, the actual fit remains quite stable. It's about the same, you can't even tell the difference, right? But with this function, you will see that the fit changes quite a lot. So as we draw new samples, your estimate is now very unstable. It varies a lot. So we say that it has high variance, but it has low bias. And we'll quantify these things more shortly, but essentially low bias means it's able to do a very good job at approximating the underlying function, but the fit is very unstable or varies a lot as you go on. Okay? So this is known as the Biasvariance tradeoff. We want a model that does well both in terms of bias and variance. We want to simultaneously optimize these two objectives. Okay? So yeah, let's look at this Biasvariance decomposition in some more detail. And before we do that, let's ask the question of what is the best fit we can get. So that's the question actually we started off when we started classification, right? We asked what's the best possible classifier you can have, and that was the Bayes optimal classifier. Right? So we can ask the same question here. Now under regression, what's the best possible fit you can have? What is the function that, so let's talk about what's the function f star that achieves the minimum expected mean square error. Okay? And the answer is actually something very intuitive. It's expected value of y given x. See why that's the case, but why is it intuitive? Because at least if you think of the signal plus noise model, right? You're assuming there's a true underlying signal and there's zero mean noise added to it. So if I look at what's the expected value of my observations, it's just that underlying function, right? So it intuitively makes sense. And we'll see that actually we can prove formally that if you minimize this expression, then this term, expected value of y given x, is your optimal predictor. Of course, you can't get to it because this requires knowing the joint distribution of x and y, which we don't have as before, right? But let's maybe work out a little bit. So we can talk about the mean square error for any function f. And I quite big. Can people in the back see? Okay. Oh yeah, the focus is a little bit off. Let's try that. Is this the right color? Okay. It's getting worse. Maybe a zooming in. Okay, so it was just about zooming in. Okay, so what we'll do is let's rewrite this by introducing the term. We actually know the solution, so it's a little bit easier to work at it this way. So let's introduce this expected value of y given x, just add and subtract it. This is one way to do it. Of course, there are many other ways. And terms together, form a square. So that's is quite intuitive is because this will help us understand the Biasvariance decomposition also. All right, so now I'm at this point, and we can just move the expectation inside, right? Because it's just a sum of three terms. So we get the value of f of x minus the mean squared plus expected value of the second thing. Get twice, and then I have expectation of these two terms, right? So one of them is expected value of y given x, and the other one is, all right. The last term, actually you can see, is Any guesses?
0.
It's 0. And how do you see that? Well, you'll notice that random. And what's random here is your test point, x and y, right? What I can do is I can write this expectation instead as expectation over x, and I can take the expected value of y given x inside, right? Hopefully people know this trick. If we take the expected value, so if I rewrite this as expected value over x, and I take expected value of y given x inside of the same quantity, which is the product of these two terms, that's, and the first of these two terms is actually does not change, it's a constant with respect to y given x, right? So I can pull that out, and I'm left with just taking, so if I have this, I can pull out, so we still have the expected value over x. You can bring this out, and now we are left with the second term, and when I take expected value of y given x of that, I get that, and y becomes expected value of y given x, right? Which is 0. Good? All right, so what we have shown, why did we do this? Because now we have shown that the expected value, the mean square error for any predictor f is equal to this quantity plus this quantity, right? The second quantity is nothing but the mean square error of the best predictor, right, of y given x. So what we have shown is that the mean square error of any predictor is equal to the mean square error of this, if you want to think of it as f star x, the best predictor, minus y, right, and plus something which is a square, right? This is just f of x minus, which is again f star x. This quantity is always positive. So we have shown that the mean square error of any predictor f is at least as large as the mean square error of f star x, which means that f star x minimizes it, right? Everybody happy with that? So we've argued that the best predictor is actually indeed the predicted value of y x. Right? Everybody okay with that? It actually has, as I said, nice interpretation in terms of the signal plus noise model. If you want to think of your generated by some underlying function plus noise, then that function f star x is indeed just its expected value of y given x, right? You just have noise added to your function, and the best predictor is when you get rid of the noise. It's the function that you will get. And what does this also say? At least under the signal plus noise model, the best possible performance you can hope to get, right? And what is that best possible performance when you are under the signal plus noise model? What does this mean square error of the best predictor look like? All I'm asking is, what does this term, so this is the best possible performance, right? Because you know that for any other estimator f, the performance has to be larger than this. So this is the best possible performance you can hope to get. And what is that? What is that best possible error you can hope to get under the signal plus noise? Say that again? Right, it's the variance of the noise, because all we have here is y minus f star x squared. Y minus f star x is just noise. So you're talking about expected value of the noise squared, which is just the variance of noise. Right? So under the plus noise model, the best possible performance you can hope to get, the best possible error you can hope to get, is just the noise variance, which makes sense. You can learn the underlying function, and all you're left for in terms of these mean square deviations is the noise variance. Okay, so I hope that makes sense. So what we have shown is, and that will lead us into the Biasvariance decomposition, is that for any estimator f, the mean square error can be written as this residual error, that's the best possible you can hope to get, plus an extra term which essentially says how far is your estimator from the best possible one. Right? These are exactly the same terms we had before, right? So the first term I wrote here is the residual term, and the second term is exactly how far f is from f star, which is what we have here. Okay? All right, so let's study bias variance decomposition. And to do that, what we'll look at is, of course, there's one, we are actually going to say that the mean square error can be decomposed into 3 terms, not 2. So we'll take this first term and we'll write it into one term that involves the bias, another term that involves the variance, and then there's going to be this third term which is irreducible. We can't hope to get rid of it. That's the performance of the best possible prediction. So we'll leave it as is. So now we'll focus on this term. This term actually decomposes into 2. One we can think of as bias and the other as variance. All right, so let's look at that. And to do that, so basically this is, I sort of wanted to clarify some more notation before we go into this. When we are talking about bias and variance, we are talking about an estimator that's learned from data, right? Not just any fixed estimator, but an estimator that's learned from data, because that's the estimator that will change your training data, right? That's what will constitute the variance. So really, when you're using, instead of any predictor f, if you're using a predictor that was trained using some data, right, then we can still look at its mean square error. Expectation is over 3 quantities. So x and y are the test points. Of course, those are random, those earlier. But we also have the expectation data, because our estimator itself is random. That's what constitutes variance. It's going to change as we change our data set, even if the data set is of the same size, right? So now we are going to look at actually, that's why actually I didn't include the subscripts here. Anytime we just write expectation, it means expectation over everything that's random, including in this case data when your estimator is learned from data. All right, so we actually look at this term, which is nothing but the term here, on how far is the estimator that we learn from data from the best possible one. And we'll decompose it like this into one term that's variance, another term that's bias. Okay, and actually maybe we can stare at it and first understand why it's bias and variance and then do the derivation. So the first, we'll show that you can write this into as a sum of these two terms. The first term is saying how far is the estimator from its expected value, right? So if I train this estimator on multiple instances of data sets and you take the mean of that, you can talk about how does any one instance vary from its mean. That's exactly talking about what we showed earlier, the variability as you change your data set, right? So this is talking about how much does my estimator vary from its average value on multiple runs. Make sense? That's what captures variance, and that's why we'll call this term as the variance. The second term is how far is the mean of the estimator, right? So if you did it on multiple draws and you took the mean of all of those, how far is that the true label y? And that's going to be bias. It's how well you can approximate your data on average, right? So at least I hope intuitively these terms, we can do the math, but these make sense, that this is capturing how good of a fit you get on average when you train your estimator on. This is saying how much does the estimator itself vary on multiple data sets, right, of the same size from its average value. How does it vary? Does that make sense? Everybody okay with that? All right, so let's quickly do the derivation for this. We'll see that we can nice decomposition into bias and variance. All right, so we start with, again, I think we can do the same trick. So we'll start with, I'll drop this subscript for now, but then we'll introduce it when. So we are talking about how far is this learn prediction. And again, what we'll do is subtract this term, which only involves looking at the mean over data, right? Because that's one of the terms we sort of want to get at. So we'll just add and subtract that term. Right? Doing the squares, we get the first term is just that squared, right? So taking this whole thing as one term, plus that minus f star x squared, right? right? And then we get, actually I might have my, I think this should be f star x. I might have this thing incorrectly because we have already incorporated how far f star x is from y, which is the noise residual variance. I think this is a typo. This should be f star x. Right? And we'll see that that's how it will come up. Right? So we have this, and we have twice the cross term. This guy and then the other one. All right. Now you can see how these terms are popping up. The first one, when we move the expectation inside, is just the variance of the data, right? It's same as this. It's saying how far is the estimator f from its mean value. The second term will lead to the bias squared. So it's how far is the estimator from the best estimator. So yeah, that's what it should be. How far is the best estimator able to approximate, on average, the underlying function f star. And we'll see that this term, or I guess I was pointing to the wrong thing, the cross term there, that's going to vanish. Will that vanish again? Because as I said, the outer expectation involves everything. It involves x, y, and the data set. So when we take the expected value over the data set inside, we see that for the second term, when we take expected value of data set, that's a constant, right? So we can bring that out of the expectation, and for the first one, we just get a 0. People okay with that? All right. So when you expand it out, you get your variance term. The bias term. And the cross term, you can treat the second part constant, or at least you can bring it out of, it will still be inside the expected value over x and y, but you can bring it out of the expected value of the data. And then we have expected value of the data of this first part. And this thing is this here. Any questions on this? So it's fairly straightforward. All you have to do is add and subtract this expected value with respect to the data, and you see that the two terms that pop out are the bias and the variance, and the cross term disappears. So again, this y should be f star x. It's the underlying function. And how far is f star x from y? That's f star x is your best predictor that we have already captured here in the residual term. All right. As you are going to use more and more complex predictors, you are going to reduce the bias, because on average your mean fit is going to fit your underlying function better and better, right? Because it's more and more complex, but it's going to vary a lot, and we saw some simulations, right, to support this. So the variance is going to be high. In fact, here's how you can think of the effect of model complexity. So here I've plotted the complexity of your underlying class. So you can think of it as going from a constant fit, a linear fit, quadratic fit, cubic fit, and so on, higher and higher order polynomials as one example. But there are many other examples of increasing the complexity of our functions, right? For example, going from linear classification to using more and more complex kernels, all the maybe radial basis function, the exponential kernel. And we see that what happens as you increase the complexity of your function is that the bias goes down, whereas the variance goes up, right? So ideally you want to, so the overall performance of your estimator looks something like this. You want to, in some sense, pick the best model that minimizes your test error, which is really the sum of this bias and variance. So it has to do well in terms of bias plus variance, or bias squared. If you usually we call this as bias squared. Okay? And so yeah, it has to be able to do well in terms of both of these terms. So this is a nice picture to think of. These are higher and higher order fits you are getting, different degree polynomials, and you want to pick the polynomial order which balances your bias and variance. How to do that is, we haven't talked about that yet, but at least you can do this decomposition and understand why you might expect that there's a sweet spot where the model is just right, and beyond that, if you use higher order polynomials, it gets the overall performance gets worse, and before it, if you use too simple model, it also gets worse. And how to actually pick it, we'll talk about maybe at the end of this lecture, or it'll be coming up soon. You already know the answer. How to pick try to get at such a sweet spot in the model complexity is by doing cross-validation or holdout. Yep. So yeah, you've already done this in your homeworks and stuff. Yeah.
So as you increase the amount of data that you have,
yeah.
Does this change? Like if the amount of data is getting really big, like big data, right?
Yeah. So yeah, that's a good question. What do people think? So this is for a fixed number of data points, right? What happens as you get more and more data points? You still have a bias variance trade-off, but the curves change here.
It seems like it would mellow out because you'll be more penalized, like your higher order polynomial example, you'll be more penalized if you're overshooting in that range.
You'll be more penalized. Shoot.
Square error.
Yes, and I guess it depends. So what happens to the bias invariance? Let's think about that. So you're talking about the overall error, and you're right that it's sort of, so the curves are actually going to, what happens to the variance? Let's think of this. Well, what happens to bias? I guess we know. Bias is independent of data points, right? It's just whatever model you pick, you get a corresponding bias, right? How well is it an approximation to your underlying ground truth function? What happens to the variance? Hopefully you will be picking a model that's more and more stable because you have more data points, right? So your overall error is actually going to be better. And actually maybe one way to think of this happens, so yeah, let's think about what happens to the training error and test error. Looking at this. Plotting training error. Training error versus the complexity of our model plot. Then let's do test error. I'll try to draw it dotted, so just to say that that's going to be dotted. So we already know what the test error does. What do people think the test error does as we increase the complexity of the model?
You mean the training error?
The training error, sorry. Training error. Yeah, it'll just keep on decreasing, right? Because you can fit your data better and better. So the training error is kind of going to go this way, whereas test error does like this. And as you have more and more data points, we actually see that the gap between these two is going to close. So your test error actually improves, and the reason being is that you can now use the sweet spot is attained by possibly by a better and better model, because your variance is actually, your method tends to be more stable if you're training it on more and more data points. Okay, so your variance curves bias remains the same. Your variance curves keeps shifting, and so your test error overall sum also keeps shifting. Right? So of course you can bring your training error down, but your test error sort of catches up, if provided you have lots of data. Yeah.
In this figure, we approach the sweet spot when the bias equals variance. Is that true?
I should write bias squared. So when they are of the same order, yeah.
It's not necessarily true that they're exactly the same,
Yeah.
right? Here the two, it's when the two slopes are the same, and here that's about the same point as when they're equal.
Right.
So one thing to point out is that even when you have big data, you still have to worry about overfitting, right? You still have to worry about the variance of your model getting too large. It's just that it happens at a different point.
Right. Yeah. So the curves shift, but of course there's still a trade-off, because it's only an n goes to infinity. Maybe you can think of,
Right.
Yeah, potentially.
My
And of course, with big data, another issue is not only do you have a lot of data, but you also have a lot of features, right? So you still are running risk of overfitting because your data is never enough given what your model is. Yes?
How do you measure the complexity of the model?
So complexity of the model in the case of polynomial fits would be the order of the polynomial. But you're right, if you are using, say, different order of regularization, for example, say for SVMs, that's one parameter, the C parameter, you can think of it as C controls the complexity of your model, right? Or what kind of kernel function you use, the more and more complex function you use controls your complexity of the model. Other examples would be, actually we haven't talked about non-parametric, there it's easier to give examples, but yeah, you'll see lots of examples of the complexity as we go further. But yeah, even the regularization parameter in ridge regression, for example, if you're not changing the model, You're still keeping your model as linear, but you're varying lambda. That can be thought of as a regularization parameter also, right? Because it's making your fit smoother in some sense.
A good example for support vector machines or other kernel methods is the norm of the optimal discriminant function, right? So if you choose a narrower kernel width, it's going to make the norm of your optimal discriminant larger, meaning the margin is going to be worse, right? So that's another example of a trade-off, right? Is what norm of discriminant you allow and what kernel width you choose, which influences the norm of the discriminant.
Yeah, so the kernel width, sure, that's one thing you can think of as the complexity. The norm, isn't it actually the error?
So if you,
or can you think of that also as complexity?
If you even if you have a very narrow, even if you have a very broad kernel width, right? You can get very jagged discriminant functions by taking, you know, 1,000,000 times one thing minus 1,000,000 times another. That'll get you a very big derivative, right? Okay. And so you can get a very wiggly function by getting a large norm.
Okay, sure, yeah, that makes sense. Yes.
Just to clarify, the green line is essentially what we're seeing is overfitting, right? As it goes to the
yes, exactly. Well, you're. Well, overfitting, I would say, is actually when you look at the training error, that says you're overfitting because your error is going down and down. So the gap between the test and training error is really what's overfitting.
Right, that's what I mean.
Yes, yeah. So overfitting is when you're driving down your training error, you're really memorizing almost your input data, but on a test point, you're not generalizing well. So that gap reflects overfitting.
What do you get a case where the error is not normally distributed? Like, for example, with a lot of survey data, people tend to underreport, like systematic underreport.
So here, none of what we did actually assumes that. I was referring to the signal plus noise model just as a convenience, but you can see that, yeah, that's why the residual error is whatever the best fit to your data is. And only under this Gaussian noise assumption, you can think of it as noise variance, but it doesn't have to be under that Gaussian noise variance setting. Everything here holds, this whole bias variance decomposition, everything holds more generally. Right? Yeah, that's a good point to at least clarify, yeah.
Is test error always larger than training error?
Test error is in expectation. So particular test data set it's not, but at least in expectation it is, right? Think of these curves as being really expected value of the mean square error, sort of, on a randomly drawn data point, yeah. Any other questions? Yes.
So the plot here is, I presume, is for the training data, right?
No, this is your test error. So that's just saying that's why this is exactly plotting this decomposition as I wrote here. This is our sort of test error, and of course you can add the residual term if you want to it, but this is actually capturing in expectation how well is your predictor, what's its mean square error actually, right? If you add in the residual term, it's exactly the expected value of the mean square error on any randomly drawn, it's expectation over all x and y you can draw, right? So it's really your test error. Training error is this what I drew here, where training error kind of just goes down and down. As you use more and more complex predictors, for any fixed number of data points, you can fit them better and better using a higher complexity model.
So the green curve here is for testing data.
Yeah, green curve is for testing data.
Is the test error the sum of the bias and variance, or the product?
So test error is actually, so yeah, test error is this quantity, which is our, yeah, we should think of this, except for this predictor f hat, right? So it's the mean square error of your predictor, the average overall, you know, the expected value of that mean square error. And you can decompose it into three terms. One is this residual error that does not go away, that holds even for the best predictor, plus the variance, plus the bias squared. So it's really the decomposition of these three terms. Is that clear to everybody? Initially we just said, oh, you can think of the mean square error of your predictor as the mean square error relative to of the best predictor plus sort of this extra penalty you pay for since you don't have the best predictor in hand, right? And then we took that penalty and we decomposed it into the variance and the bias. So really, your original mean square error consists of three terms: bias, variance, and residual. Okay, any other questions on this? All right, good. Okay, so with that, let's move forward. So now you have some understanding of how to think of this bias and variance and how to think of model complexity, at least what effect it has on your fit, both the test error and the training error actually. So with that, let's go ahead and look at some other nonlinear estimators, right? So we talked about polynomials as one examples, but really the polynomials is just, more generally you can think of it as you're still trying to do linear regression, but with these sort of nonlinear features, right? Or you can think of it as actually regressing with some basis functions that are, for the polynomial case, are just actually x, or this is a constant, so maybe 1, x, x square, x cube, and so on, right? Forms a basis. You can write any polynomial as a linear combination of these functions, right? So this is what combination with these basis functions, 1, x, x square, and so on, is a good basis for your polynomials. But there are other basis functions you can use as well that are used to represent other classes of nonlinear functions. Examples include the Fourier basis. So if you have a periodic function, then you might want to use, you can write those or decompose those into a linear combination of different sinusoids or right, of different frequencies, right? So again, you can even throw in the, I guess, the bias term, which is all constant, and then a low frequency term and higher frequencies. Now you get a linear combination, you're learning a linear combination, which is a good fit for periodic functions. Or you can even do wavelet basis, right? So that's again another type of nonlinear basis functions. The class of functions you get after linearly combining many of these is functions that are nonlinear, but they're supported over small regions, right? So as opposed to Fourier, which tries to approximate very global periodic functions, wavelets are a good representation for approximating functions that are supported over small regions, possibly at different scales. So you can use a linear combination of these to approximate your underlying function, which could be a sized nonlinear function. These are just some more examples, just like the polynomial basis, right? And just like you control the complexity here by looking at the order of these polynomials, here you can control the complexity by looking at, for example, the frequency content. You don't want very, very high frequency components in your linear combination, because then you'll get, you might overfit, right? Your function is going to wiggle too much and try to overfit the data points. And similarly here, it corresponds to looking at finer and finer scales. So if you see the original wavelet is defined over the entire domain, and then the next wavelet is over half the domains, or the next set of wavelets is over half the domain, the next one is defined only over quarter domain, and so on. So you don't want to include very, very small perturbations. And again, by penalizing how many such basis functions you use, you can control the complexity and your model. Okay. So these are nice representations, and sort of these are, in some sense, you have a better handle of how to control the complexity here, right? Because you just control how many terms you include. But in general, throwing in any nonlinear features here, I think we briefly last time, you can be creative in whatever, but of course it gets harder to control the complexity and do model selection in this case, right? In fact, we'll see a way to do that using kernels in a minute, actually. So you can be creative and still you learn for linear regression by just realizing that now you are talking about multiple features for each data point, and those form your A matrix, and similarly the X, which is a test point, you again throw in this set of nonlinear features. And as you're throwing in more and more features, you typically won't be doing this. You will be doing the regularized version, right? Okay, so with that, let's talk about trying to get at the benefits of, in some sense, or the approximating power of these nonlinear features. Approximate better and better functions in a simple way using kernel did for SVMs, right? So how can we do that? Well, what we can do is, well, let's first look at ridge regression. So as I said, in most of these cases, when you are writing out a long list of features, then you want to do regularization. So we will be talking about this particular version, which was actually, we called it ridge regression, if you remember, right? We had motivated it from saying we want to now impose a prior on our coefficients betas, right? So these weights, betas, we had put a Gaussian prior over it, and that's how we had derived this version, which was the ridge regression version of linear regression, with this added diagonal component. So we'll look at this and we'll see a way to kernelize it. So we can, of course, put in lots and lots of features and still talk about this ridge regression and that with these nonlinear features. But a better way to do it is by kernelizing it. And how do we do that? So you can see actually that there's a simple way we can take this solution and we can rewrite it like this. Looks almost the same, except you'll notice that what we are inverting sort of has changed a little bit. So first, why can we do that? And there are two ways to go about it. First, we'll see an easy way, and then we'll see a more maybe interpretable. So the first way to do it is, I hope I get this right, is let's look at times, let me quickly refer to my notes here. Yeah, one way to do it is let's look at this quantity times A transpose, right? You'll notice that what we can do is, or actually, no, that's not what I wanted to look at. I want to look at this. A transpose A plus lambda I, right? The term I had in my original solution, ridge regression solution here. So let's look at that term times A transpose. You'll see in a minute why we are doing that. Now I can actually write this, I can pull out the A transpose up front and rewrite it as A transpose plus lambda I. Fairly easy to see why. You can actually expand it and try to do it, right? And what we'll do now is actually let's take the inverse, because after regularization, this thing is invertible. That's able to write the solution here like that. And we end up with this, right? And then let's now multiply it on the right hand side with, again, the inverse of this quantity times y. And the reason I'm trying to do that is because we are trying to get at this, rewrite this in an equivalent way, right? So now I have A transpose A plus lambda I inverse times A transpose, and I want to get a y here, right? So what I'll do is multiply this side and that side, so both sides. Here I have the A transpose, I'll multiply this with A transpose plus lambda I inverse times y. And so I get back A transpose y here. This is my original beta, right? And I've just shown that this is equivalent to this other form, which is right here. Okay, so at least this is one way. We'll actually see that duality is a better way and maybe it gives you more intuition into the problem. So we'll also do it that way. But why would you want to rewrite your solution this way? How does it help? Any thoughts? A hint, think about what we are inverting. What was the dimension of the matrix you were trying to invert here? So if you remember, actually A is right here. So it was number of data points times number of features, right? That was A. So what we had here was a number of features times number of features matrix that we were trying to invert, right? But instead of A transpose A, if we can write it as A transpose, now what do we have? We have a number of data points times number of data points matrix, right? So depending on if you have fewer data than number of features, which is typically the case, especially when we want to go to these long list of nonlinear features, then doing it this way is easier, right? And so that's one thing again. Another thing actually is think kernels. Does this ring a bell? On how? That was the case even here. You can think of everything in front as essentially it's basically a vector. You can think of it as, right, as a set of weights that are multiplying y. So that's true for both the cases. You can still think of this as linear combination of y's, this also as linear combination of y's. But by rewriting it this way, one thing we get, of course, is that we are inverting a potentially smaller matrix if n is less than p. Another reason is that now you can actually kernelize it. And the reason being, when we have A transpose, what do we have? Every A transpose is the inner product between your data points, right? So we can take those inner products and throw in a kernel there. Of course, we still have the A here. What will we do with that? This is just a list of your features for all your training points. But notice that we never really care about beta hat. We never care about estimating these regression coefficients necessarily. All we care about is the prediction, right? And the prediction is x times beta hat. So now we are taking this x, which is a set of features point, and multiplying it with A transpose, which is the set of features corresponding to all the training points. And all we have is now in a test point and the training points. So we can again replace those by a kernel. So we can kernelize the whole thing. Okay, so let's look at it. So the two reasons why we might want to do that is, one, we only need to invert an n by n matrix instead of the feature by feature matrix. Or more importantly, this kernel trick where we can directly write our prediction. We can replace x times A transpose by a kernel matrix which computes the inner products between the nonlinear features of your test point x and the nonlinear features of each training point. And similarly, this A transpose we can replace by the inner products between all your training points. Right? You can kernelize the whole thing and just work with these kernels directly. We never really have to write out these high dimensional vectors. In fact, they can be infinite dimensional. Right? We couldn't do infinite dimensional here because this would be infinity times infinity matrix we are trying to invert. Whereas here we always have this n by n matrix no matter how many features you have. It could be potentially infinite. Does that make sense? Questions? So hopefully you have seen this before, the kernel trick, and this is not entirely new. That's why I put everything on one slide. But it's digestible? Okay, good. All right, so here is now what we get is a kernelized ridge regression solution, right? So our original solution, this was ridge regression, and what we have now is this form, which directly gives you the prediction. You don't get the coefficient necessarily back, but you get the prediction directly, and it's just involves kernels that you can work with. And examples, as Jeff has mentioned before, include polynomials of degree exactly d or degree up to d, and Gaussian, and you can throw in other hyperbolic kernels and so on. Right? So these are examples you have seen before. But let's now look at this problem also from actually duality perspective. Okay, because you have seen it for SVMs, right? So again, going back to the ridge regression, this was our original problem, right? We were trying to do this least squares, minimize the mean square error with a penalty that depended on the norm of the beta vector, right? And that's how we got this solution, and we just proved that it's equivalent to this. We'll try to get at this another way, and that way you will also see actually the correspondence between ridge regression and support vector machines. You'll see that they're actually solving something very similar except for a different loss function. And so we can do duality for ridge regression just like you did duality for the support vector machine. All right, so let's look at that. So what's the similarity with support vector machines? Let's look at the primal problems in the two cases. So what I'm going to do here, this was the ridge regression primal problem, right? But we can rewrite it in a form that matches the SVMs a little bit better. So what I can do is I can define these variables zi, which is yi minus xi beta. And now I can write my primal problem as minimizing over both beta and z's this quantity, right? So all I've done is redefine these as z's here. Make sense? And hopefully you can see that this resembles support vector machines quite a lot, because this was the expression you had for support vector machines. You again had a set of linear weights, and you were penalizing their norm, right? In fact, that's what you were trying to minimize, right? Which corresponds to the norm and the beta square here. You had, so the C, the regularization term, there appears in front of the first term. Here it's in front of the second term. And what you have is sum of these psi's, I believe, yeah, hopefully, chi or psi, one of these two, xi's, okay. Yeah, I always forget these Greek letters. But you see that that's just a different loss function. Here the loss function, in fact, maybe I could have just written these as zi's and defined the zi to be square of these. So then this is a square loss function, and this is your, what was this loss? Hinge loss, right? So support vector machines were minimizing this hinge loss, right? So it's just a different loss function, and you still have the same kind of regularization. You're still fitting these set of linear parameters between the two problems. And in fact, what you have now is just like SVMs. I'll magically pull it out of the hat to show you the dual problem. But instead of solving over these original variables, like in SVMs, we can do the same thing as we did for SVMs and now try to solve over a different set of parameters where there's one parameter, one alpha I per training point. So the advantage of going to this dual version is that these were p-dimensional, right? The beta was p-dimensional, and now we have n-dimensional problem you're solving. This is another way to see how you can go from that p-dimensional solution, this one, to sort of this one that involves n-dimensional inversion, matrix inversion. All right. In fact, we can see that if we have this dual problem and we can solve it. So you can take the derivative of this problem with respect to alpha, set it equal to 0. I won't do it, but you can see that you get something like this as your solution, alpha hat to this dual problem. And you can actually back your beta hat from that, which is, so just like in SVM, linear combination, your W hat vector was just a linear combination of all your alpha i's times there it was your input data times the y i's were also there. Here it's just a linear combination of your input training points. So you can think of alpha as the weight of the training point, how much it influences what your regression coefficients are. All right. And once you throw in the appropriate, you write the sum as a inner product and then throw in what the optimal alpha we got was, you see we get at the same solution which we had derived earlier, which involved this n by n dimensional inversion. So you actually get it using duality theory as well. And the nice thing, the one interpretation it brings about is sort of this interpretation. Think of your regression coefficients as some weighted combination of your input points, right, where the weights are given by the alphas, the dual parameters. The one difference is that in support vector machines, these alphas were typically sparse, right, and that helped you define the support vectors. But in ridge regression, these are actually, there's no reason they are sparse. The sparsity really arose from the inequality constraints we had in SVMs, and here you don't have that. So the alphas are just some set of weights, they may not be sparse. All right, so here's one way what duality buys you, as I said, is to think of the regression coefficient as a linear combination of your input data points and your alternate derivation of the solution. But also think about what the prediction is. So our prediction is x times beta hat, right? And if you write that out using this form, you see that all you have is that your prediction is just a linear combination of the inner product between your test and training points, right? Which is a nice interpretation. In fact, in the kernel now you can think of the kernel version of that. All you have, similarly you can show, is this inner product is replaced by a kernel. So what you're doing is your prediction is just a linear combination of these kernel evaluations between your, how far is a training point from your test point. Your kernel is sort of measuring that, right? It's a measure of similarity between your test point and your training point. You measure how similar a point is, and you give it some weight, and you take a linear combination. That's your prediction. Okay. If you want to think of it, here's another way. You can think of the prediction as a weighted sum of bumps, where the bumps are your kernels, right? Because you can have like a Gaussian kernel or something, and then here's your training point, yeah, right? Different training points, and here's your test point. Then all you're doing is sort of putting a kernel, your these little kernels on top of your training data points, scaling them up by alphas, and then just summing those values up at your test point. You're summing the values of the weighted bumps, and that's your prediction. So it kind of gives you a nice interpretation for once you go into this duality theory of what's going on. All right, questions on this? Okay, so with that, there was just one more topic I wanted to cover, which is an interpretation talked about kernelized ridge regression, right? How you can rewrite your solution in this form and then you can kernelize everything, right? So your final prediction can be done in terms of kernels. One question you might wonder is, well, ridge regression was derived by thinking of putting this Gaussian prior on your weights, right? So what about kernelized ridge regression? Can you think of that? What's the prior you're using now in some sense? Okay. There you had this fixed set of weights, right? You had D weights corresponding to each of the D features or P features, whatever you want to call it. There was one weight for everything. In the kernel, what we are doing is we are not taking this, we are approximating a function not by a line, right? But by these very infinite dimensional features in some sense. And we are now putting a prior on what that infinite dimensional function looks like. Okay, so let's think about what's the prior in kernelized ridge regression. So again, going back to recall that ridge regression was obtained when we said, well, why is like f of x plus epsilon, where epsilon is your Gaussian noise, and then we said f of x is linear, and we put a Gaussian prior on the betas, right? That's how we had got ridge regression. Now we are asking for kernel ridge regression, what's the prior? And here's what the prior looks like. So this is exactly like, if you remember how the kernels were introduced in discriminant functions, right? You had your decision boundary. Initially you had a set of D weights for the decision boundary, or as many as number of features. And then you said, well, we'll think of this boundary as not being indexed by D features, but by it's an infinite dimensional so you can think of that as your discriminant function, and you got it by doing something similar to what we'll do here. We'll think of f now as it's not a line characterized by D features, but it's an infinite dimensional representation, infinite set of points that we are using to represent it, and we can impose a prior on f. So instead of saying f is x beta and beta has a prior, we can put a prior on f, and we'll say that f comes from a Gaussian process, which is an infinite dimensional process. What that means is if I sample f at any 2 points xi and xj, then the covariance between those two is just sigma ij. Okay, so it's saying if I take 2 points, right? Here's my line function f. I take 2 points here, xi and xj. Then the values here and here, how similar they are. This sigma tells me how similar they are, or the correlation between these 2 points. So this is the prior that's been used in kernel ridge regression. It's a Gaussian process prior, where you think of your function f itself as coming from, right? I haven't told you what the connection with kernels is, if that's the question, but you need to hold on. Okay, go ahead.
Why do they have to be 0? The mean has to be 0?
They don't have to be, just like here we believe that all of these coefficients are 0, so we'll put this prior. Here's another prior you can put on your function, and in this case you'll see that you actually get a nice correlation with kernels. You don't have to. You can put in any other mean as well. This is just, yeah, it doesn't, you can put a different, it's just whatever prior belief you have, right? So it's not necessary that you put in a 0 for your function.
If you do want to use a non-zero mean, you could just subtract off the mean.
That's another way to do it.
The remainder would have a prior that had 0 mean. Right, so
but yeah, you can throw that in. There's no preventing you. And in fact, you might want to do it here, because here it's still, well, I don't know which one is more justified. Yeah, right. You can throw it in if you want.
If you have the training data, you take the sample mean of the training data, and then the variance of the training data, and that would be your Gaussian process. Can I do that?
I don't
think
think
that's determined from your data cannot be part of your prior.
Right. Prior is something.
General rule. Prior is before you have data.
Right.
Now, that's like, don't worry about that yet.
Prior is the posterior. So you don't want to base your prior on data. Prior is just something you come up with. But here you're right, you can in fact have a mean specified as well. I just put it to the covariance, what ties it with the kernel actually. But you can, yeah, put it. All right, so yeah, what connection does this, I said, well, you put this Gaussian prior and now you get kernel ridge regression back. What does the kernel and the covariance have to do with each other? It turns out that the kernel between 2 points is exactly the covariance between the corresponding points. So whatever covariance you specify your Gaussian prior is actually, you can interpret the kernel function as the covariance under a Gaussian process prior. Okay, so if you pick a kernel, you can think of that kernel as whatever kernel choice you have given is equivalent to putting a Gaussian process prior on your F with that covariance specified by the kernel. All right. And we'll actually see why that's the case. So why? So this is still repeating the same model that we had, putting a Gaussian process prior on F. Why do we get that the kernel is same as this? Well, let's just focus on what our model is here with this prior, and let's look at what we get for our solution, right? So first let's look at what is the joint distribution of our training data points. So remember this bold y is y1 to yn, that's the set of your observations, and f of x, which is what you want to do the prediction for, right? If you look at this set together under this model, how is it distributed? So it's easier to first think about y. Let's think about how is f of x1 through f of xn and f of x. What's the joint distribution of that? Well, that's what the Gaussian process prior is telling us, right? It's saying that if I take any two values, right, if they are distributed like Gaussian and their covariance is given by the sigma ij's, right? So this is distributed as a big Gaussian with mean 0, and if I want to, the covariance is just sigma, right, corresponding to all of the values, sigma i's and the j's corresponding to points. I just want to break it up into this so that we get this. I want to sort of treat these points separately from this. Ultimately, we are going to be interested in predicting f of x for the test point, right? So I want to look at its distribution separately. So if you look at this, I can write this as some sigma nn, which is every element is sigma between xi and xj, right, as given by our Gaussian prior. So I'm just using this as a shorthand notation. Sigma xn and sigma xi, right? So this, for example, corresponds to sigma between x1 and x, sigma between x2 and x, and so on up to sigma between xn and x. Okay. So all I've done is I've taken my sigma matrix corresponding to all the training points and the test points and blocked it up into this form. Right? So that's what this looks like under this Gaussian process prior. And what's the distribution of the y and f of x looks like? Well, y's are just the same to the y part. Make sense? You can go through it more. That's all we have done is taken this distribution of the f's and we have got the distribution of the y's by realizing you're just adding IID Gaussian noise. Right? So this is how our joint distribution looks like of our observations, observed labels, and the one we want to predict. Right? And now we can talk about what's the posterior distribution. This is just given by the prior, right? Posterior distribution of f of x, which is the quantity we want to predict given our observations y. Right? And it's a nice rule that I won't derive. You can do it yourself, or you can, if you would like, we can cover it in the recitation. You just have to request it. That if you have a multivariate Gaussian vector, right, then you can write, which is sort of blocked up into these two. In our case, it's blocked up into, actually we care about y and of f of x, where y is y1 to yn. And if this is jointly Gaussian, then we can write out where, say, the mean is 0 and the covariance, as we said, is this. It's blocked up into 4 values. Then we can, if you take conditional distribution of f of x, again a Gaussian, and it has a mean and covariance which is given by these formulas right here. In fact, you'll notice that this is just the Schur's complement, if you know what that is, of the matrix, of the covariance matrix here. So that's the conditional distribution of some set of variables based on other set of variables for a jointly normal vector is also Gaussian, and it has this mean and this covariance. And you can try to work it out, or we can do it in a restriction. But now your posterior distribution is also Gaussian. So if I have to now come up with a prediction for what f of x should be, what is the prediction? We do the map estimate, right? So this is the posterior distribution, and what's the value which maximizes the posterior distribution here? It's a Gaussian distribution. What's the value that maximizes the Gaussian? Same as the mean, right? So our prediction is just this. Say that our map estimate of what the label of f should be, f for f of x should be, is just this quantity right here. And now you can see that this looks very similar to what we had for kernels, right? For kernel, we had something like the kernel between our test point and all the training points, and the kernel between all the training points. Here we get now the covariance between the test point and the training points, and the covariance between all the test points. So you get exactly the same expression. You can think of the kernels as specifying a covariance between the points, or actually as specifying a prior on your, a Gaussian process prior on your function itself. Right? So this might seem a lot, but it's just saying that just like we had a prior for ridge regression on the weights, now we are not talking about linear functions. We have weights to put a prior on, but we can put a prior on the entire function we are trying to learn, and that prior is this Gaussian process prior, where the covariance is given by whatever kernel you choose. That's, if you don't understand, you follow the math, you can try to go through it slowly later, but just getting to the gist of it, that what's the prior with kernel ridge regression that we are using? The answer is Gaussian process prior with the covariance specified by the kernel. Right? Now if you want to see examples of things drawn from this prior, here are, what does this Gaussian prior look like? Here are three functions that are drawn from that Gaussian process, just with mean 0 and whatever covariance was chosen. Here are three examples. These are the prior to any data being observed, just due to the assuming this Gaussian 0. Actually, in this case, it was 0 mean. And if you actually look at the online slides, you will see a bar here with standard deviation also. You just can't see it for some reason due to the projector. And then you see that these are the functions that are sampled from the posterior distribution. So these are three functions sampled from this distribution, and how they look like. So you can see that how they are governed by the data points. So here you had 5 data points based on which you computed the posterior, and that's how the, and again you see that there are here in some sense, if you look around the mean, the Gaussian process has equal variance for all. So the standard deviation around it is about the same for all points, and here based on the data point it changes a lot. So again you'll have to look online. I'm sorry these colors are not being reproduced here well, but your data governs how your posterior changes, and now the functions drawn from it also change, and they can be quite complicated. And you also saw this for EMs, how those different discriminant functions look like. So yeah, there's no shaded region. You can't see the shaded region. There is no. You'll see it online. And there's a nice reference to Gaussian process priors if you want to learn more. All right, so with that, let me summarize. What we talked about today was polynomial regression and regression with nonlinear features. And then we looked at kernel regression and its interpretation in terms of a Gaussian prior, right? And also, these concepts are important. We talked about the model selection and how Biasvariance decomposition gives insight into what model we should select. In a future class, we'll talk about cross-validation and those things in more detail on how you pick the model. All right, that's it.